our last class, we talked about a very special kind of subgroup known as normal subgroup, and few properties related to normal subgroup. We talked about one of the very most important theorems of group theory, especially for finite group theory, known as Lagrange's theorem. Lagrange's theorem. So it's very important theorem. And if you remember, the theorem states that for a finite group, let G be a finite group, let G be a finite group, maybe commutative, maybe non-commutative, maybe cyclic, doesn't matter, any for any finite group. Let H be a subgroup of G, H be a subgroup of G. As G is finite, of course, H has to be a finite subgroup. Then order of H must divide order of G. Okay, so that's the basic definition of, basic statement of Lagrange's theorem, and you'll find plenty of applications of Lagrange's theorem throughout our algebra course. Okay, so today we are going to talk about another very important concept of abstract algebra known as homomorphism. So we'll be talking about homomorphism. So it talks about, so meaning of homomorphism intuitively like similar kind of shapes. Okay, so we'll basically talk today about the similarity. So the question is, what do you mean by a similarity? Okay, so for example, suppose I draw one triangle and I draw another triangle. And if I ask you a question, is this two, are they similar? So question is, are they similar? Are they similar? So there are, how you are looking into the question, it depends, depending on that, your answer will be many types. For example, you can say that, okay, they are not similar because maybe their sizes are different. Okay, but if I ask you the question, are they similar with respect to the geometrical shape? Yes, both of them are triangle. So in that respect, you can say that these two objects are similar. So when we talk about similarity, so some underlying assumption or underlying modeling should be there, right? So if I ask you the question directly that are these uh, two images similar, you say that, okay, this looks like little smaller than this, so they are not similar. But if I look into the viewpoint of geometric object, then both of them are triangles, so they are similar. Similarly, if I considered, say, Q, within this Q, rational numbers, and if I consider, say, 9 by 3 and 3, okay, so in Q, rational numbers, if I consider 9 by 3 and 3, and if I ask you this question, are they similar? Of course, your answer will be different types depending on the understanding that you are thinking or the point of view that you are actually focusing on. So somebody will say that, okay, here we have used different symbols, different kind of notations, and here no other symbols, so of course they are different. But if you look at from mathematical viewpoint, because you all know the definition of rational numbers, with that respect, if you think of, you will say that, okay, they are exactly the same. 9 by 3 and 3 are exactly the same. So here also we have some kind of underlying observation or underlying system. Based on that, the answer will be different. Somebody will say that, okay, they are similar. Somebody will say this is not similar. So it depends on your how you're looking into the question. Okay, again, there are different types of looking at the similar questions. For example, again in Q, we know that we can define an equivalence relation on Q defined by some A by B is related to C by D if and only if AD equal to BC. So we know that this is an equivalence relation. Equivalence relation. Okay. And as a result, it makes a kind of partition on Q that we all know. Okay. And here, half and 2 by 4, they are similar because they satisfies this property, and you can see that this is half can be thought of a leader of this set as a half, 2 by 4 or 3 by 6, they are all similar. So you can understand that this equivalence relation on a set may also give you or may also induce some kind of similarity. So as we are dealing with this abstract algebra course, so suddenly here we will also think about the similarity with respect to the algebraic structure. So here we have already seen that we start with a non-empty set G along with some kind of operation, say composition. And G along with this composition, if it satisfies few of the properties, then we called this together as a group structure. So it's nothing but a kind of algebraic structure. Okay. Now, if I want to find kind of similarities with respect to this algebraic structure, then what kind of objects or what kind of mathematical justifications that we can provide? Okay. For example, let us consider two groups, Z plus and say Z2 plus. So you all know what do you mean by Z2 plus. So Z plus consists of say 0 plus minus 1 plus minus 2 and so on, whereas this consists of only two elements, class 0, class 1. Okay. So if I consider from algebra viewpoint, few algebraic properties like it is an infinite group. So this is a finite group. So here it has many elements having finite or infinite order. Here no element of infinite order. Okay. So you can think of infinitely many, infinitely many, infinitely many subgroups. Here finitely many subgroups. It is a commutative group. Commutative. It is also commutative. It is cyclic. It is also cyclic. So it's also cyclic. So how many generators it has? Z plus, how many generators it has in Z plus? Somebody?
Two.
Two
One and
generators. 1 and minus 1. Here how many generators are there? Here how many generators are there? Quickly, how many
one.
generators? Only one.
One.
One generator. Very good. So you can see that there are plenty of properties which are algebraic properties. You can also share another. There are many others. For example, it consists of infinitely many normal subgroups. Infinitely many normal subgroups. And how many normal subgroups are there here? Exactly how many normal subgroups of Z2 are there? How many normal subgroups?
Two.
Exactly two. Very good. Exactly two normal subgroups. Okay. So you can see that there are plenty of similarities and plenty of dissimilarities. For example, it is a commutative group, it is a cyclic group, so they are similar, but there are plenty of other algebraic properties which are different. Okay, now let us try to find more similarities. Okay, so suppose this is my z plus and this is my z2 plus, and z2 plus is quite little less, 0 and 1. Okay, in z plus, how can you justify, can you give me some algebraic property within z plus that can be mapped into 0 and 1? Any idea, any basic thing that you can think of, some properties of integers, the whole
So
collection of
if
properties can be.
if
Yes,
even then it goes to zero, and if odd then it goes
very
to one.
good. So we can think of z as a collection of two things, so even integers and odd integers and nothing else. So take any integer, that integer may be either even or odd. Now let us try to map all even integers to 0 and all odd integers to 1. Now what is the justification why I am trying to give in a kind of map so that some properties is satisfied? Okay, first very important observation that we can think of. So even plus even, what it is giving? Some even number plus even number, what it should give? It's an
Even.
even. So even plus odd, it becomes
Odd.
odd. Odd. Similarly, odd plus even becomes odd, and odd plus odd gives me even.
Even.
Okay. Now this plus is actually this plus, same plus. You can understand this, same plus. Okay. Now here also, if the same thing is happening, so here even goes to 0 and even goes to 0 and it gives me 0, the same thing. Okay. Similarly, even means 0 plus odd means 1 gives me odd. Similarly, odd plus even gives me odd, and odd plus odd gives me even. See, all this with respect to this plus. So here we are talking about the similarities of algebraic structure with respect to this operation. So algebraic, so if I consider only z, then z is nothing but a set. But when I have addition over z, then altogether they form some algebraic structure. So in that algebraic structure, we can see that we can divide the whole set into two halves. One is even integer, another one is odd integer, collection of even integers and odd integers. And if I have a kind of mapping, so how the mapping could be defined now? So mapping from z plus to z2 plus. Now you can understand, you are matured enough that this plus and this plus are not the same. This plus is addition with respect to modulo 2, whereas this plus is the addition of integers. Now how should I define this? So f of n equal to class 0 if n is even, and equal to 1 if n is odd. So now you can understand that we defined a function, but we can always define a function. What's so great about it? Now you'll understand that, okay, if I define like this, then at least some properties of with respect to this algebraic structure is satisfied here. Okay. Now if you look at, if is even, so this is a function, no doubt about that, and it satisfies this property. Suppose I consider this to be plus, just for the sake of distinguishing between plus and this plus, I make it a plus with circle. Now you can understand that, say, take any two integer n1 plus n2, what is fn1 and fn2, and if I put equal to, then what should I give here? So you can understand that fn1, so if this is my f, then fn1 will be an element of z2. So within z2 the addition is plus with circle. So here the plus with circle should be there. Now let us check whether these are satisfied or not. Okay, how do I check it? So first take any n1 plus n2 and then check whether this is same as this or not, and that will be clearly followed through this. See, n1 may be even or odd, but it cannot go out of this all four options. So this could be the all four options that n1 and n2 may take. Whatever be the case, depending on this case, it will be either even or odd something. So this value will be either even or odd following some of these rules. Whatever may be the rule, it will go somewhere here, and you can understand that f1 will be something like this and f2 will be something like this, but that will be suddenly among this. It cannot go out of this. Okay, so as a result, what you can understand that this property is satisfied. Okay, so let us try to prove it formally. So what I need to prove is, suppose G is one group, say G star, and say H is another group, say G composed. Okay, F is a mapping from here to here, then F is said to be a homomorphism. F is said to be a group homomorphism if G1 star G2 equal to F of G1 composition F of G2 for all G1 G2 belongs to G. Okay, how it looks like? It looks like this. Say here you have G and H. So here you have G1 and G2. If you make a function over F, then this will be, say, F of G1 and this will be F of G2. Now F1, sorry, G1 star G2 is also an element of G. Now if you apply F on it, so it will be F of G1 star G2. Now these two elements are element of H. So what operation is there? Closer, this one. So F of G1 composition F of G2 will also be an element somewhere, say here. Now if it happens that they are equal, that means first you have G1 G2, make G1 G2 star, then apply F on it, so it will be F of G1 star G2. Now another way you can think of, you have G1, you have F of G1 here, similarly G2 here, you will have F of G2 here, and then with respect to this operation make a composition of FG1 composition FG2. So this will also be an element of H. So you have FG1 star G2 element of H and FG1 composition FG2 as an element of H. Now if it happens that they are equal for all G1 G2 belongs to G, then we call F as a group homomorphism. Clear? Idea is clear? Any question? Okay. So let us try to find some examples. Okay. So we have already seen that if from z plus to z2 plus defined by f of n equal to class n for all n belongs to n, for all n belongs to z, is a group homomorphism. Why? So f of n1 plus n2, by definition n1 plus n2, and we know that within this z2 it happens like n1 plus n2. Okay, for all n1 n2 belongs to z. So this property is satisfied. As a result, so this is same as f of n1 plus f of n2 for all n1 n2 belongs to z. So we say that f is a group homomorphism. Well, okay. Now suppose I have two arbitrary group G say star and H dot. Can you define a homomorphism? You do not know anything about G and H, just two arbitrary groups with some having some arbitrary operation. Can you find a group homomorphism between these two? Any group homomorphism? Anybody? Any group homomorphism that you can think of?
So identity element is identity element.
No, identity to identity will be not a homomorphism, because for homomorphism you need to define a map from G to H, and in that case it should be defined over all elements of G, not only one E, right? Okay, but your direction of thinking is perfectly okay. So this is E of G and this is E of H. Now maybe what he wants to say that he is going to define f from G to H by f of x equal to E of H for all x belongs to G. So I think he wants to define in this way. Okay, could you please check whether this is a homomorphism or not? Question: is f a group homomorphism?
Yes.
Okay, somebody says true, somebody true or false. Somebody says true. Okay, why? How will you define? How will you prove it?
Because if we take two elements x1 and x2 from G1,
Okay, very good. Let
um,
x1, x2 belongs to G. Then
G, then
what is the value of fx1?
EH.
EH, same as fx2.
Yes.
Now f of x1 star
Star
x2
x2
equal to again
E of
E1,
H.
E of H, very good. Same as E of H composition E of H, same as f of x1 composition f of x2, because all these values are E of H. Okay, so that is true for all x1, x2 belongs to G. That implies f is a group homomorphism. Clear? So that means what it says, this is very important. That means this homomorphism sending all the elements, that means what is this? This is sending all the elements to EH. That means geometrically it will look like this. All elements will go to EH. Okay. So this is always there. So to know that, you do not require any special property of G and H. So this kind of homomorphism, group homomorphism, is always there. So this is the identity homomorphism. Every element is goes to E. So this is a kind of very trivial homomorphism. So this is called trivial homomorphism because it's always there. Trivial homomorphism. So the question is, can we have some non-trivial homomorphism? Can we have always, suppose any other group homomorphism, is it like always possible that we can always have a non-trivial homomorphism? Okay, let us try to check. So previously we have defined our F from Z plus to Z2 plus, right? Now let us try to reverse the ordering, okay, like this. So G is a mapping from Z2 plus to Z plus. And I want a non-trivial homomorphism. So the question is, can you find a non-trivial group homomorphism from Z2 plus to Z plus? So what is your guess? Any guess?
Sir, I think no.
Okay, why? So can you find? Somebody says no and yes. Okay, and your answer is no. So my
Sir,
question
no
suddenly,
হবে sir.
okay, why? Why? A very
Sir,
simple
because
question.
domain
ডোমেনই তো স্যার মানে দুটো এলিমেন্ট আছে,
Yes,
কিন্তু
yes.
কোডোমেনে স্যার অনেক অসংখ্য এলিমেন্ট আছে।
Okay, so domain consist of two elements, and codomain consists of infinitely many elements. So do you think that that would be a problem?
Actually, the one element does not map to the more than one element.
So it may happen that 0 class 0 goes to 0 and class 1 goes to 1. Then that would also be a function f. The question is whether that would be a homomorphism or not. That's a different issue, but you can always define a function. So it's not required to exhaust all the elements of this. I never told you to have an onto mapping. I just told you a homomorphism.
Sir, I think, sir, it is not a function, sir.
Okay, so you say that this is not a function. Why not?
Sir, here uh, 0, 0 goes to 0. Again, 0 go, again 1 plus 1, and f of 1 plus 1.
So you are talking about this function.
Yes, sir.
Okay, so you are talking about this function only.
Yes, sir.
Okay, okay. So 0, so you say that 0 equal to 1 plus 1. Yes, then what is the problem?
Sir, if it is homomorphism, then, sir, f of 1 plus 1 is equal to f of 1 plus f of 1. F of 1 plus 1 is equal to 2 f of 1. And f of 1 plus 1 is equal to 2. F of 1 plus 1 is equal to 1 plus 1 is equal to 0. So f of 0 is equal to 2. So 0 goes to two elements, sir, 0 and 2.
Okay, but I tell you that this is just a function. Okay, but my question is, can you find some? So you may have some different function. So here I have defined like this, but you can also define like 0 goes to 4 and 1 goes to 7. So what you need to show, somebody says that there exists no function, non-trivial function, mind that. So trivial function is always there, right? Everything goes to 0. So that is always there. But my question is, what should be some non-trivial function? Can it be? So somebody says no. Okay, then somebody must give some rational or reasoning that why it is no. Okay, let's see. Uh, Suppose there exists some homomorphism A from Z to Z2, which is non-trivial. So this is non-trivial homomorphism. Non-trivial homomorphism. Okay. So okay, so it's other way around. Z2 to Z, right? It was Z2 to Z. Non-trivial homomorphism F. So f of 0 say goes to x1, f of 1 goes to x2, right? So we know that 0 class 0 plus class 0 gives you class 0. So in terms of if you make a homomorphism of it, so what we will have, f of class 0 plus, I'll just cut it down from here, f of class 0 plus class 0 should be equal to f of class 0, right? That implies what is, by homomorphism property, you will have f of class 0 plus f of class 0 equal to f of class 0. So if I put these values, so x1 plus x1 equal to x1. What does it mean? What is the value of x1?
0.
X. So x1 equal to 0. Okay. Now we also know that 0 plus 1 or maybe 1 plus 1 gives you 0, right? You can think of this 1 plus 1 equal to class 0. That is f of class 1 plus f of class 1 equal to f of class 0. That means x1, this is, sorry, this is x2 plus x2 equal to x1, and x1 value is 0. Okay, that means what is x1? Sorry, what is x2 then? X2 equal to how much?
Also 0.
Also 0. So what we have proved then formally, that whatever be the function, if you consider, see, I haven't done anything, so it's a completely general form. Suppose there exists a homomorphism from Z2 to Z, then suddenly 0 element will go to somewhere and 1 element will suddenly go to somewhere. And after doing few steps, what we found, that whatever be the case, f of 0 will go to 0 as well as f of 1 will always go to 1. What does it imply? What is the meaning of that?
Trivial group homomorphism.
That is, f is a trivial group homomorphism. Okay, so that's very important. So here means, if I consider G to this, then only trivial homomorphism exists. But if I have, in this case, how many homomorphism can you think of? At least one non-trivial homomorphism that you can think of, right? So even goes to 0 and 1 goes to, sorry, odd goes to 1. So that is a non-trivial homomorphism. But if I change the direction, then you can understand that the situation may change. So here you have at least 2. So till now what we have shown, that So this trivial homomorphism will already be there, and a non-trivial homomorphism, that is even goes to 0 and odd goes to 1, is also there. So at least two homomorphisms, but here you see that if I change the direction here, then there exists only one homomorphism. So the important point is, if a function f from g to h is a homomorphism, that does not imply that the opposite side direction will also hold good simultaneously. So this is a kind of example where you can see that if you change the direction, then the homomorphic properties may vary. Okay, clear? Okay. Let's come to another interesting observation. Okay, suppose consider, say, okay, now quickly tell me this. Okay, after some time maybe. So let us define a mapping like Z to, okay, maybe from little bit, say from S3 to Z6. Okay, so in my previous example, left side or right side, maybe one of them were finite, another one is infinite. So here this is finite, this is infinite. Now I am talking about both of them are finite. So S3 to Z6. Can you find a homomorphism from S3 to Z6? Any homomorphism can you think of? Okay, so you can always give me one, at least one homomorphism. Tell me one homomorphism. How should I define? F of some element A goes to trivial homomorphism, that is class 0 for all A belongs to S3. So this is already there. Now can you find some non-trivial homomorphism here? Some non-trivial group homomorphism here. Okay,
Say order
since
of 2 in
very good. So in terms of, if I look into the whole scenario in terms of order, then we see that E is an element of order 1, then 1 2, 1 3, 2 3 are elements of order 2, and 1 2 3 and 1 3 2 are elements of order 3. So they are order 3 order elements, they are order 2 elements, and this is order 1 elements. Okay, now in Z6 let us try to find where it should go. Okay, so if I consider class 0, class 1, class 2, class 3, class 4, and class 5, quickly can you tell me what is the order of 0? It is 1. What is the order of 1 in
6,
Z6? 6.
6,
What is the order of 2?
3,
3. Order of 3?
2,
2. Order of 4?
3,
3. Order of 5?
6.
6. Very good. Now, so what you need to do, you need to define a function from here to here. Mind that you need to exhaust all the elements from here, because it should be valid for all the elements of the domain. So you need to take care of all the elements, but on the right hand side, it may not go to each and every element. Okay, now tell me, where should I send f of E? Where should I send f of 1 2 and f of 1 2 3? Any idea? Any idea? So maybe I put
say
it
f of
f
t
of
goes to
1, I put it f of 2. Okay, another homomorphism I'm trying to construct. Okay, yeah, f of E goes to where?
0,
Okay,
class 0,
0. Okay, 1 2, where should I go send him?
say class 3,
class 3. Okay, and this one
Class 2.
class 2. Okay, so 0, 3, 2. Okay, let's check whether anybody else would you like to give some idea. So he has given one kind of function on his own. Let us try to check whether that is a group homomorphism or not. Okay, so here if you look at this order is 1, this order is 2, and this order is 3. Okay, in that way he has given a kind of ordering. Okay, so let's have a look at what is happening if I have this, say 1, 2, 3, composition 1, 2, 3. So f of this should be equal to, if this is a homomorphism, then it should be, so what is this? It should be f of 1, 2, 3 plus f of 1, 2, 3. If this is our homomorphism with respect to this f2. So if I consider this f2, then f2 of 1, 2, 3 composition 1, 2, 3 equal to, if this could be a homomorphism, then it will satisfy this property. Or f2 of, what is this value? So 1 goes to 2 and 2 goes to 3. So 1 goes to 3 and then 3 goes to 1 and 1 goes to 2. So this value. Okay. This is equal to, what is this value? 1, 2, 3 value is 2 plus 1, 2 value is 2. Okay. Or, so what is this? So now you also need to define the values of, because if this is a function, it has to be defined on all the other values. So you have till now defined on only on 3 elements, e 1, 2 and then 1, 2, 3. So what's about, say first let us try to define this. What should be 1, 3, 2? Can you tell me what should be?
Class
Class
4.
class 4. Okay, and this order is 3. Then what should be 1, 3 and what should be f of 2, 3? We shall find it soon. So that means if you defined f2 like this, then this is your class 4 equal to class 4. So apparently there exists no such confusion, right? So this is passed, but till we need to define this two. Okay, so the question is, how do I define this two so that it should satisfy the property of homomorphism? Tell me what should be the value of f2 of 1, 3 so that this becomes, f2 becomes a homomorphism. So if you have already defined 4 elements, only 2 elements are required. So class 0 is already gone, class 3 is already gone, class 2 is already gone, class 4 is already gone. So you have exhausted 1 order elements and 3 order elements. So you have now just now defined the, now what, which elements are remaining? So 6 and 1. But mind that you may not require to define each of the distinct elements. Okay, now what should I write here? So you have already taken 4. Okay, so your elements then 0, 3, 2 and 4. Okay, let
Say
us try
f2
to,
of 1, 3 also class 3, and last two are both class 3.
last, this is both class 3. Okay, then let us try. Okay, let us try. So both of them are ordered. So this is order 2, this is order 2. Okay, so if I consider say 1, 2, 3, say f2 of 1, 2, 3 composition, say 1, 3. So according to, if this could be a homomorphism, then it should be 1, 2, 3 composition. So this is plus F2 of 1 3, right? So what is this value? F2 of what is this value? 1 goes to 3 and 3 goes to 1. So 1 goes to 1, 3 goes to 1 and 1 goes to 2. So 2 3, right? So this is 2 3 equal to what is this value? F1 2 3. F1 2 3 is class 2 plus 1 3. 1 3 is class 3, or what is this 2 2 3 was your class 3 equal to class 2 plus class 3. So at this point of time you get a big contradiction. So you understand that it should not be the case. That problem is might be here. Okay, then so I just try to give you a basic kind of motivation so that you can do on your own by using some rough idea. But if I tell you the theory, then you will be able to understand that you cannot proceed like this. Okay, so any other try? So he has tried a nice one. Any other try? Anybody? Any other try? So where should I put? So you understand, if I consider F2 like this, then it cannot be a homomorphism. It could be a function, and you can understand that this is a it's not a bijective function because it's not injective, but it's still an function, and it's an onto function, no doubt about that. So this is an onto function, but this is unfortunately not a homomorphism. Okay, let's anybody try with some other. So F2, where should I put it? So F3, now it's my F3 maybe. Okay, let's put it in a different way, maybe here. So F3, our again new try. So F3 of E, F3 of 1 2, F3 of 1 3, F3 of 2 3, F3 of 1 2 3, F3 of 1 3 2. Okay, so anybody, let's try.
Sir, F3 of E, sir, 0,
Okay, 0,
3,
okay,
3,
3,
3,
oh, 3, very good,
0, 0.
0 0. Okay, so he has given a kind of idea of even permutation and odd permutation, right? So that at your mind that is playing. So this is even permutation goes to 0 and odd permutation goes to class 3. So this is odd, this is odd, this is odd, this is even permutation, this is even permutation. So even permutations are going to 0 and odd permutation is going to 3. And you can check that with this it forms a group homomorphism, because what is happening here also, like my previous case, even plus, so even composition even, what it gives, if you have one even permutation, one odd permutation, what it will get, you will get even or odd, you will get even or odd. If you
Sir,
have
even.
even permutation, so even odd, what you will get,
Odd.
odd permutations. So odd even, you will get odd, odd composition odd gives you odd. Why? So odd means odd number of transposition, here also odd number of transposition. For example, suppose it is like 1 2 1 3, say 4 5. Okay, maybe say 6 3 and 4 5, and say this is say again an odd, say 7 8. So here odd permutation, this is also odd, but when you are making composition of this, how many of them? So 1, 2, 3, and 4. That means even, even. So not odd. This is even. So yeah. So even, sorry, odd, odd gives you even. Clear? Now it will be very easy for you. So for even, you are getting 0, and for odd, you are getting 3. So even, even. That means 0 plus 3, sorry, 0 plus 0, 0 plus 0, you get 0. Even means 0 plus odd means 3, you get class 3. That means odd. For odd, that means class 3 plus even 0, you get odd. And for odd, class 3 plus class 3, you get class 0, because we are in Z6. Mind that we are in Z6. So we are in Z6. That's why class 6 is equal to class 0. So through this, you can understand that this actually gives you a group homomorphism. So this is a group homomorphism. Okay. So a homework, a standard homework is find all group homomorphism. Group homomorphism. So I have shown you two, at least two you can. So this is the non-trivial one, and trivial one is already there. Find all group homomorphisms from Z6 to Z, sorry, Z6 to S3. S3 to Z6. Okay. So I want all group homomorphisms from Z6 to S3 as well as S3 to Z6. Okay. So this is will be your homework. So you please tell me in my next class. Okay. So now I am going to give you a little bit of theory, and there you will able to see that now it will be, if you know the theory, then it will be easier for you to understand. So first thing, suppose if from G to G, G to say H be a group homomorphism. See, I am just ignoring the star or dot, etc. So everywhere I'll just put dot, or sometimes I don't give any symbols in between two elements. So be a group homomorphism. Then what is the value of EG? Now you can understand what should I write it here. F of EG should be what? What should I write? Any guess?
EH.
Very good. E of H. Okay. Second is maybe F of A inverse should be what element? What should I
F
write
of A
here?
whole inverse.
F of A whole inverse. Very good. 3. If F is, sorry, if G is commutative, if G is commutative, if G is also so, true or false?
Sir, false.
Okay. First of all, I wrote F of G. So the question
Sir,
is, what
H,
do you,
it should be H.
True, sir, true.
okay, so I wrote F of G. Then the question is, what is F of G? F of G is nothing but the image of G under F. Okay, that means all such elements from H. So all such H belongs to H such that there exists some G belongs to G such that F of G equal to H. That means this is called image of image of F. Okay, image of G using F. So it is denoted by also image of F. So F is the homomorphism. That's why. So image of F, or image of G using F, that means denoted by image of F. So what is this property then? F of G. So you can think of like this. Suppose this is a group. Say this is G and this is H. So image of F. That means this is this portion and this portion as a kind of, this has the onto portion. That means for this every element here, for every element H, so this is an element of H, no doubt. There exists some G such that if you make a F on it, so Fg an element of H, that must be equal to H. Clear now the definition? So the question is Fg commutative? True or false now?
Yes, sir. Commit.
Okay. So commutative, when I talking about commutative, so it must be a commutative group. So the first thing is that image of F is a subgroup of whom? Subgroup of
H.
H. And then it should come, if G is commutative, then this is same as image of F is also so, and that is true. Okay, let us try to prove this. The first one, how to prove the first one? How will you prove F of, so first F of EG, you can write F of EG dot EG, and by homomorphism property, this is F of G, F of EG. Now, so F of EG equal to F of EG dot F of EG. So by cancellation law, or you can, so this is a group. So inverse of every element exists. So if I multiply both sides by F EG of whole inverse, then what you will get? You will get the left side, what you will get? E of
H.
H equal to F of EG. Is this step clear to all of you? Because I am multiplying both sides by this inverse. So from this, what I am doing? I am doing multiplying both sides by F of EG of inverse into F of EG equal to F of EG whole inverse into F of EG into F of EG. Now you have the associative law, so you can have these two together. So what is this value? So this is an element of H, this is an element of H, and inverse of this is this. So what will be the result? The result will be the identity element of H. And by associative law, this is also, if you make a product, that is also identity element of H. And if I have a composition with identity element of H and F of EG, both of them are element of H, so you will get back this. So you have this result. Is it clear? That means all my examples, wherever I started, if you look at, all the elements goes to identity element, goes to the identity element here. So if somebody starts with like this, E goes to 3, then at that point you can certainly say that it can never be a homomorphism, because if this is not the identity element of the group which is on the right side. Okay, that means identity element will always go to the identity element of the other group. So you can see that wherever we started with, we did the same thing. So even goes to 0. That means here the even means within that even 0 was there, and here the zero element is the identity element. So 0 goes to 0 everywhere. Wherever we did this, we followed the same rule. Okay. Then the next property. The next property is, what is the inverse of this? So if some element A inverse. Okay, so let me write A inverse of if some element you take, make an inverse, and then put an inverse of it. Okay, so pictorially it looks like this. You have A, then you have A inverse, and F is a homomorphism from G to H. So you have FA, you have FA inverse here, you also have FA of inverse. Okay, so all three elements are elements of H. Now what is this value? According to the theorem, what we have already written, it should be FA whole inverse. Now the question is, how do I prove this? The proof is also very straightforward. How do I prove this? Anybody please come out of this. So something, this inverse of this is this. So what does it mean? So A and B, they are inverse of each other. What does it mean? You need to show that this should be equal to E. That's all. So here all the elements, they are from H. So that means you need to show that is equal to E of H. That means, so this, then what we said, then A inverse equal to B, right? So this inverse is this. So what you need to show? You need to show that FA into FA inverse should be equal to your E of H, and the other way around. And also F of A inverse into F of A, that will be equal to the same thing, EH. If we are able to do so, now consider this to be A and this to be B. So this is your B and this is your A. Then what you say, that A inverse means if A of whole inverse equal to B, what is your B? Your B is this. Okay. So if I able to prove this, then we are done basically. So the proof is very simple. Left hand side, start with left hand side. Left hand side equal to FA into FA inverse. And this is a homomorphism. So F of A into A inverse. So this is F of E of, what should I write here? E of what?
G.
G.
Very good. And just now we have seen that this is nothing but E of H. Similarly, we can also show that F of A inverse into F of A. That can also be shown. So the result is proved. Okay, clear? Okay, the next one we're going to prove is, this is a subgroup of H. That means image of F. What does it mean? That means all such H belongs to H such that there exists some G belongs to G such that F of G equal to H. Okay, or you can simply write it in this way, F of G such that G belongs to G. You can also write in this way. So it's all the image of G, it consists of all the images of G. So we need to prove this is a subgroup of whom? Subgroup of
H.
H. Okay, now tell me what to do. How can I prove this? Formal. Step 1, what should I show first?
Closure.
No,
This is not empty, non-empty.
very good.
Because
So
if
many
it is
times I
empty,
told you that the first step should be, that first step of a group is, it should be a non-empty set. So first you need to show that image F is non-empty. How will you prove that image F is non-empty?
f of eh equals to f of eg equals to eh.
Very good. So EH equal to f of EG belongs to where? By definition. So any element which is belongs to G, and if you take a f of that, then that will be in f of H. So that is within image of F. Because what is that image? Because here it is your G and this is your H, and you are sending all the elements, whatever is there, G, G1, G2, whatever may be, you must set f of G1, f of G2 and so on. So this is the collection of all such elements on which f is applied. So here this is my element from G and on which f is applied, and it belong, so this must belongs to image of f, and this value is EH, so EH must belongs to image of f. That implies image of f is non-empty. Okay, very good. Then next step. Next step, somebody. Somebody please. What should I do when I need to show something is a subgroup of something? Say this is H. So I have shown that this is non-empty. Then take two elements, say AB from here, and show that AB inverse is also within K. So take two elements. Let elements are looking like this. So let F G1, F G2, where G1, G2, so this belongs to image F, where G1, G2 is from where? From where? It should be from G. Okay. Then if G1 into if G2 whole inverse, that is equal to, please tell me now, what should I do?
F g1 into f g2 inverse
If G1 into if G2
g2
inverse, just now we have shown. So if G2 whole inverse is nothing but f of G2 inverse, and then f of
f of g1
G1, G2 inverse.
G1 G2 inverse, because it's a homomorphism, and then
belongs to image of f,
It is belongs to
because
H.
g1 and g2 belongs to g, as g1 g2 inverse belongs to g.
very good, that this belongs to image of F, because this belongs to G. Clear? So yeah, so this is belongs to F. So as we started with two elements from here, we show that this into this inverse is also within image of F. That implies image of F is a subgroup of each. Clear? Okay. So that's very important. Now when you understood this, now it will be easier for you to assign these elements. Now you assign these elements in this way, you can understand what is, in this case, what is my image of F. Can anybody tell me what is my image of F in this case? So this was a mapping,
Cycle and p-cycle.
F3 was a mapping from where to where? From S3 to
Z
Z6. Now what is my image of F?
0, 3.
So
0, 3. Very good. And you can understand that image of F is a subgroup of my Z6. So this is a subgroup, no doubt about this. Clear? So now you understand that when you are going to assign something, so in my previous example, you are going to assign, so in the previous example, who tried? His try was really good, but unfortunately it didn't work. One of the reason behind this was he has given how many elements? 0, 3. So if this could be a homomorphism, then what would be image of F2? Image of F2 will consist of 0, 3, 2, and 4. Will that be a subgroup of Z6? Can it be a subgroup of Z6?
No, sir.
No, sir. Why? Very good. Why?
5 does not exist.
The closure does not hold.
Closure doesn't hold. Not only that, this is not even a subgroup. See, if this could be a subgroup, then that must divide the order of the group. So this order is 4 and this order is 6. So 4 cannot divide 6. So now you can understand in many problems, you will be able to apply the Lagrange's theorem. So since by Lagrange's theorem, if this could be the image of F2, then that cannot divide Z6. The order of this cannot divide the order of Z6. As a result, this cannot be a subgroup of Z6. As a result, this can never be a homomorphism, because just now we have shown that if this could be a homomorphism, then image of F2 must be a subgroup of this. Clear now? It's clear? Very good. Now I am going to show you another very important definition, and that definition is called kernel of F. It's very important. In many problems, you will find this term kernel of F. Kernel of F. Kernel of a homomorphism. It is defined by, so image was just now we have seen that if this is your homomorphism and say GH are two groups, then image is here. So this is your image. But kernel is something which is a subgroup of G. Mind that. So kernel is all such elements G belongs to G such that F of G equal to the identity element of H. That means if I draw again, so this is your F. So we are considering all such elements from that group G to H such that if EH is the identity element, all such elements from a set which actually moves to E, that is known as kernel of F. So that is the subset. So this is a subset of G. Clear? So all such elements from G, if you apply F on those elements, that will go to identity element of H. So this is a subset of G by definition. First property that I am going to prove is that kernel of F denoted by car F is a subgroup of whom? Subgroup of
G.
G. Very good. Now prove this. Prove this result. How to prove that? How will you prove that? Step by step. Tell me
So non-empty.
how. Very good. Non-empty. How?
Sir, identity must go to
Okay.
identity.
So as f of E G equal to EH. So that means EG follows this rule. That implies EG belongs to kernel of F. That implies kernel of F is non-empty. It's very good. Okay, then you need to prove A B inverse, right? So take two elements. Let A B belongs to must be equal to how much?
EH.
EH equal to F of B. What do we need to show? To show A B inverse belongs to kernel of F. Then for that, what do we need to show? Then F of A B inverse. What is this? F of A into F of B whole inverse. Just now we have seen what is this? F of A is EH into EH inverse, that is E of H. That means AB inverse also follows the same rule as in definition. That implies AB inverse belongs to kernel of F. That implies kernel of F is a subgroup of G. Clear? Okay. So we are going to prove something more. Car has specific extra property, and that property is kernel F. Car F is anybody can able to tell me? Is a
Normal.
Normal
very
subgroup.
good normal subgroup of G. Okay. So how will you prove that? How to prove that car F is a normal subgroup of G?
If you take a element from kernel F H,
Okay. So what you need to prove? So this is my kernel. So say take any element H. Let H belongs to kernel F
and G
and
belongs to G,
G belongs to G. Then
then then F G H G inverse
very good. What you need to show to prove G H G inverse belongs to kernel of F. So to prove this, what you need to show, you can put F, you can apply F on it, and it should go to the identity element of H, right? So then that let us try to check what is this value. Yes, then
F G dot F H dot F G inverse.
Fg of inverse, right? And what is this H? Since H
E
belongs to kernel of F, then F of H must be E of Fg into E of H into Fg whole inverse. So this value will be Fg whole inverse, and if I then Fg into Fg whole inverse, ultimately it gives you E of H. That implies kernel F is a normal subgroup of G. Clear? So in many cases, you will need this property. Okay. So now you can understand when I ask you find all homomorphisms, find all group homomorphisms from say, okay, so from say S3 to Z6. So what you understand, so then you can proceed in this way. Let F from S3 to Z6 be a group homomorphism. Then kernel F is a normal subgroup of S3. Now, if you know how many normal subgroups are there, then what would be your conclusion? If you know that there exist, how many normal subgroups of S3 are there?
3.
3. So you know that S3 has 3 normal subgroups, S3, E, and A3. So you can understand that for every homomorphism, kernel will be a normal subgroup. So that means if it has 3 normal subgroups, then the number of group homomorphisms cannot be more than 3. if it would be more than 3, then that kernel should be a normal subgroup, and which will contradict the fact that it has exactly 3 normal subgroups. Is the statement clear? So this kind of important observations will be very much important for your many competitive exams, that kernel is a normal subgroup of that group, and that will help you in finding how many subgroups or how many normal subgroups are there for a particular group to another group. That will help you a lot. Okay, so is it clear to all of you now, this part? Okay, then I will talk about, maybe in my next class I will talk more on it, but in this class I will show you another kind of similarity. So we tried to find out a similarity with respect to this algebraic property. That means if it is a homomorphism, then this algebraic operations are preserved. That means even plus even goes to right hand side. That will also satisfy the similar property as we have already seen. Now let us try to find uh, another kind of special kind of similarity. For example, if I consider Z4 plus this group and Klein's 4 group. Klein's 4 group. So you know what is Klein's 4 group. So if I draw this table, then it is, if it is star, then E, A, B, C, right? So E, A, B, C, and it gives also E, A, B, C. And what are the elements? The elements are E, then A, B, C, A, E, A, A, E, A, E, E, C, and then B, and then B, C, E, A, and this is C, B, A, E, right? So this is the this table for the star with respect to the Klein's 4 group. Now, if I consider the similar property with respect to this, then we know that this is my plus, and here my class 0, class 1, sorry, this is my class 1, this is my class 2, this is my class 3. Okay, here also class 0, class 1, class 2, class 3. Okay, so another one I will consider, another group is the fourth root of unity. So you remember this group, all such z belongs to C star such that z to the power 4 equal to 1. That means it consists of plus minus 1 plus minus I. Let us try to again formulate that table. So here we have some dot. So 1, this is minus 1, this is I, this is minus I. So 1 minus 1, I minus I. Okay, so let us fill this up. So this is your, I am not putting the class. So 0, 1, 2, 3. This is 1, 2, 3, 0. This is 2, 3, 0, 1. And this is 3, 0, 1, 2. Right? So they are all classes. I'm not putting classes. And can you please fill it up, this one? So this is 1 minus 1, I minus I. This is minus 1, 1 minus I. This is I minus I minus 1, 1 minus I. This is I This is 1, this is minus 1, sorry, minus 1. Okay. So we have drawn 4 tables. So what is our aim? I want to find, so the question is, can you find some group homomorphisms from any two of this? So from here to here, from here to here, from here to here. So here you will have all, so you need to choose 2 of them. So 3 out of altogether 3 of them. So the question is, how many, if I consider this is G, H, and this is K. So the question is, how many group homomorphisms can you find from G to H, maybe from H to K, and maybe from K to G, and the other way around. So initially it was G to H, and then from H to G. Okay, but one thing you will able to observe here, that okay, if I consider this is my these two tables, then one thing you should observe that it has a special kind of similarity. Let's see where the 0 element stays here. That means where the identity element. So this is the identity element. So identity element stands here, 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 here. Let's see where the identity element stands. What is the identity element here? Who is the identity element here?
1.
1. So 1 and then 1. Okay. Then this 1. Maybe here 1, here 1. See that these tables are not exactly the same. And where this identity goes? Here, 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 here. Okay. And see that here there is a similarity. 3, 3, 3, 3, 3, all here. Here, C, 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 all here. But here, this is not the case. Oh, here also the same case. Minus I, minus I, minus I, minus I. Okay. So almost the same case. But I'm saying that there is a difference between the similarities. Let's check. The first question is, can we change a bit this so that this table and this table could have a similarity? Can we change a bit so that these two tables could have a similarity?
फोर्थ कॉलमটাকে সেকেন্ড কলামে নিয়ে যাওয়া
Where? For whom?
স্যার
This one, this
ফর
one.
this first one.
Okay, first one you want to change the
Fourth column to the second column.
fourth column to the second column. That means you want to change this two. This two.
Yes, sir.
Okay, why you want to change this two?
Sir, actually I want a pattern, want a similar pattern between the first two groups.
Okay. Okay, let's check what will happen. So if I change like this, then what will happen? Okay, so the first will be remaining the same. So 0, 1, 2, 3. The this one first and second and what you told? Second and fourth. Okay, that means 4 will come here. That means 3, 0, 1, 2. Okay, then here it will come 1, 2, sorry, 1, 2, 1, 2, 3, 0, and this will remain the same. That means 2, 3, 0, 1. Okay, and then do you think that the same pattern is coming here? Same pattern is coming here also?
First and third That they have a same pattern, I think.
First and third, they do have a same pattern. No, they do not have. So here this is C, but here this is 1 3 1 3. So they don't have the same pattern. Then okay, let's try another drawing of the same. This one. So this is 1, instead of -1, if I put say I, then -1 minus I. So 1 I -1 minus I. And let's have a look. 1 I -1 minus I. And then I -1, then minus I, and then 1. -1 minus I, 1 I, minus I, 1 I, -1. Okay, now can you find something? This one and this one. So here you see that 3 3 3 3 3, and here my minus I minus I minus I minus I. So kind of, okay, let's see here 3. Okay, sorry, not this. So this 3 3 3 3. This is my minus I minus I minus I minus I. Let's check with this one, maybe with black. I'll put maybe with blue one. I'll put say 0. So 0 is here. All zeros are here. So here, if I put 1 here, 1 and all ones are here. Similar pattern. 1 and then all 1. I mean 0, then all 0. So here 1 and then all 1. Let's about 1 here. Let's take a green one. So 1 1 1 1. So here I I, and 2. 2's are here, and then last one. So -1 are here and last one. So what do you think that? Find some homomorphism from Z4 plus to ±1 ±I with respect to dot. Can you define now? Is it now easy for you to define? So what should I send? Class 0?
1.
1.
It is always 1 due to the homomorphism. So this is 1. And then class of 1, where should I send him?
Iota. I.
I.
I. F of class of 2 goes to where?
-1.
-1. And then F of 3 should go to -I. Look at here. Who are the generators here? In this group, who are the generators?
I and minus I.
So plus minus I. So they are the generators. And C, who are the generators here? In Z4, class 1 and
plus 3.
class 3. See, generators are going to generators. Generators are going to generators. The orders are also preserved here. The order of this was 1. It goes to an element of order 1. It was an order 4. It goes to an element of order 4. This is 4. This order is 2. It goes to an order of 2. Its order is 4. It goes to 4. But if you consider either of this table with this K4 or this, you never find this kind of similarities. That means you have here more similarity than in K4. So my homework is you will able to understand that if you are finding all possible homomorphisms from these groups, so you'll have 6 options, right? So I need all homomorphisms from this group, then the idea will be quite clear to all of you. And this kind of questions are quite frequent in many of the competitive exams starting from JAM to TIF for exams. So please go through this chapter, homomorphism, group homomorphism, and what I am talking, this special kind of similarity or more similar than this is known as isomorphism. Isomorphism. And in my next class, I will talk about this isomorphism, and you will see that homomorphism, you have a certain kind of similarity, but isomorphism means is more similar. And you will find that two algebraic objects are isomorphic means they will have exactly the same algebraic properties. In my previous examples where we have shown that few properties are same, but there are plenty of properties which are different. But in case of isomorphism, you will able to see that all these properties will be same. So here in this case, we had a homomorphism, but only these two properties were satisfied. But all the other properties were not satisfied even though we had a homomorphism. So this kind of similarities are there, but there are many ways where they are not similar. But when we talk about isomorphism, we will show that they are exactly the same, and you can expect many questions in any of the competitive exams from this isomorphism and homomorphism part. So they are very important from exam viewpoint, and also they are very important from abstract algebra viewpoint. Unless you understand those things, you won't be able to proceed further. So they are considered to be the pillar of this kind of abstract algebra. If you have any question for the question, you are free to ask me. If not, then I'll stop it here and I will teach you next in my next class the isomorphism properties.